All right, so today we are going to get into graphing these quadratic functions. I keep mentioning it. Now we're going to finally get into how to actually do that. And we're going to graph it when the function's in standard form. So like this, y equals ax squared plus bx plus c, or y equals ax squared plus c. There is a different form called vertex form that if we don't get to in here, your Algebra 2 class will get into. But we're going to focus on standard form here. So, some definitions for you really quick. A quadratic function, you already know this. It's a function that looks like this. Now, a function has to have two variables in it, an x and a y, usually. It maps x's to y's, inputs to outputs. So anytime you see x's and y's, that's a function that can be graphed. And since we've just got finished solving quadratic equations, then you know that you've seen this before. Y equals ax squared plus bx plus c. When we did quadratic formula, we picked out a, b, and c. Well, a, b, and c, when we graph, is going to be in the exact same spot, right? The degree of a quadratic function is degree 2 because it's got a square, right? The x squared. Now, every function family has a parent function. Linear functions, quadratic functions, square root functions, exponential functions. These are functions you'll talk about in Algebra 2. But they all have parent functions. And what a parent function is the simplest version of that function. And this is it right here. So y equals ax squared, but even more to the point there, the simplest version is when a is 1. So y equals x squared would be the parent function. We'll talk about an adjusted parent function when a is something other than 1, but that's your parent function, right? Every other function can be created from that parent function. Okay? And again, standard form of a quadratic function is where y is on one side by itself and all of your other terms are on the other side. So we got to separate them out. Kind of like y equals mx plus b. We want y by itself, right? All right. Next is a parabola. You've heard me use that term before. Parabola is the U-shaped graph that we get when we graph a quadratic. So like this. This is a parabola. Okay? It does U. It can U up or down. And we'll talk more about that as we go through this. So it will have a bottom to it or a top to it, depending on how it opens. Now, axis of symmetry. So every parabola that we graph will be symmetrical. You should be able to fold it over on top of itself, and it should match up, right? The axis of symmetry is the line that divides the parabola into two matching halves. So if we go back to this graph right here, the axis is, if I wanted to fold this graph over onto itself, we would fold it basically right down here through the middle. Okay, that would be your axis of symmetry. Now the axis of symmetry is a line. It's a line that we're going to draw through and cut the parabola in half. Okay, so since it's a line, the way we describe it is to use the equation of that line. And since this is a vertical line that's going to cut the parabola in half, remember Vux. Vux tells us that the equation should be x equals wherever that line hits the x-axis. Right now it's 0. So that would be your axis of symmetry. And we'll always write the axis of symmetry as a line. The next definition for you is a vertex. The vertex is that highest or lowest point on the parabola. The axis of symmetry will always go through the vertex. The vertex should always be on the axis of symmetry. Right? So if we go back to this guy right here. Now what you don't see in this graph is the fact that this U does extend up forever. So here and here. So there's not a highest point because this parabola will go up forever. But there is a lowest point, and that's this guy right here. And so this is your vertex. Okay? Since the vertex sits on the axis of symmetry, right? That means that the x-coordinate will always be whatever this axis of symmetry is equal to. Right now, it's 0, right? The coordinate for that point right there is 0, 0. Now, the y-coordinate could change, depends on the function, but the x-coordinate for the vertex should always be the same as whatever the axis of symmetry is equal to. We'll talk some more about that in a second. Okay? But some definitions for you here that you need to know. Okay? All right. Now, since the vertex is the highest or the lowest point, the vertex will lead to either a minimum or a maximum value. Right? So the definition of a minimum or a maximum is whatever the y-coordinate is for those points. Okay? It's going to be the highest point if it opens down, and it's got to be the y-coordinate. It's because that's the value of the function. That's what we get when we plug in x. Right? The y-coordinate will tell us that. So we go back to this, and since the vertex is the lowest point, then we're going to have a minimum. And since the y-coordinate of this particular point is 0, the minimum value is going to be 0. Now, it's not always going to be 0. The vertex will move around. We'll talk about that some more as we get into graphing this guy. Okay? And maximum was just what you would get if it were to open down. Okay? All right. So, how do we know if the graph is going to open up or open down? It's a great question. There's multiple ways you can explore this. But basically what it boils down to is if that leading coefficient, if A is positive, then the parabola will open up. If it's negative, the parabola will open down, right? So for example, in this first one, this guy is going to open up because A is positive 1. The second guy, A is negative 2, so this guy's going to open down. And that's going to be helpful for us as we start trying to get a sense of what these graphs look like. Okay? A will tell us some other things as well. Now, if A is bigger than 1, so this means the absolute value of A. So regardless of sign, whatever the sign is on A, if A is bigger than 1, then believe it or not, the parabola will get thinner. So instead of looking like this, it will look something like that. Right? If A is less than 1, now it's the absolute value of A is less than 1. So it's not if it's negative, it's not negative 2. I know negative 2 is less than 1, but the absolute value of negative 2 is positive 2. What we're talking about when A is less than 1 is if A is something like a half or a third or 3/4 or whatever. When it's basically a decimal less than 1. Then the parabola will open up wider. So instead of looking like this, it might look like this. Okay? So it's kind of opposite of what you might think. If A is larger, then it will get thinner. If A gets smaller and smaller and smaller, then it will get wider. Okay? So, take a look at these guys right here. This first example, is the parabola going to open up or down? And is it going to be wider or thinner? We can always compare it to if A is 1, right? So take a second and think about that, and then we'll go through the answers. Okay, well, this first guy is going to open up, right? Because A is positive. It's positive 4. But since A is 4, then this is also going to be wider than, let's say, the parent function where A is 1. The second guy? Second guy is going to open down because A is negative. And since A is a half, then this guy is going to be, you know what, I messed that up. This guy is going to be wider. Sorry. We'll go back and fix it. This guy is going to be wider. So if you're thinking over here, Mr. Smith's crazy, you're right. this graph is going to be thinner than it would be if A was 1. The graph on the right would be wider than, say, if A was equal to 1. Okay? All right. Let's move on. Now, we will talk about shifts, but we're really going to talk more about shifts in terms of the vertex when we learn how to find the vertex. But one thing that you can kind of pay a bit of attention to is whatever C is. C will tell you how the parent function will shift. How does the graph shift compared to the parent function? So since this guy is -4, then that means it's going to shift down. The graph's going to shift down. And since this one is +2, it means this graph is going to shift up from the parent function. But we'll really use it more in terms of the vertex, what the vertex is. Okay? All right. So that's a lot of sort of just getting a general idea of what the graph's going to look like. Here's what we're going to do to graph. Okay? First thing we got to do is get it in standard form. It's like solving a quadratic equation by factoring or the quadratic formula. We got to get it in standard form. Then we're going to pick out what A, B, and C are. Okay? Then we're going to go ahead and graph what I like to call the adjusted parent function. So the parent function is y equals x squared, where A is 1, but we'll graph where y equals whatever A is. We'll include A in that adjusted parent function because we're going to take that adjusted parent function and then move it around, right? We will use that adjusted parent function to fill in an xy table. We'll just choose some x's and plug in and find out what y is. We'll graph and mirror across the x-axis. Okay? Because it's symmetrical, we'll just do the same on both sides. Then we got to find the x value of the vertex, and this kind of got messed up. We need to pull this down. The x value of the vertex comes from this equation right here, which is opposite b over 2a, which looks a little bit like, well, not like, it is part of the quadratic formula. So that's how we're going to find the x-coordinate for that vertex. A lot of reasons why that's the case, but we won't worry about that right now. We just got to remember that we got to do opposite b over 2a to find the x-coordinate of our vertex. Once we've got that, to find the y-coordinate, we can treat that like an xy table. Just plug in the x value to the function and see what y is. And we're going to want to know what the vertex is. That's what's going to tell us how to shift the parent function that we will have already graphed. Okay? So it seems like a lot of steps, but once we get into it, I think it'll make a lot of sense and it won't be that bad. Okay? All right. So, for example, here's a function that we want to graph. And we want to get a sense of what this is going to look like. So, is this guy going to open up or down? Well, if you look, it might be helpful to go ahead and pick out A, B, and C first. Since this guy is in standard form already, we know that A is going to be 1, B is going to be 4, and C is going to be 5. Since A is positive, then this guy's going to open up. Okay? Okay. Next, since A is 1, it really shouldn't be wide or thin. It should be kind of like the sort of a standard sort of shape to it. But our next step here is to go through and graph the parent function and use this xy table for the parent function. We can even label it. Okay? The parent function, which is going to look like y equals x squared. And the adjusted parent function would be that we would use whatever a is. But since a is 1, we'll leave it like that. Okay? And I might go ahead and have you add a few rows to this to get as many points in here as we can to see what's going to happen, right? So now, the parent function. And to find out what this looks like, we need to just pick some x values, plug it in, and see what y is, so we had some points, okay? Now, because I've been graphing these for a long time, I know the best numbers to use right? And actually, let me back up. Let's not add 2 rows here. I don't think we're going to need them. But I'm almost always going to default to 0, 1, and 2, right? So over on the graph here, I want to find out what happens when the graph is here, here, and here. If I can find out what the graph looks like there, then I can just mirror image over to the other side, which is why I took away the 2 other rows. We don't need to do 2 rows if we're just going to mirror over to the other side. So 0 is part of the domain. It is the possible x. So if I come down here and I plug in 0 for x, I get y equals 0 squared. 0 squared is just 0. So I know one point on the graph is 0, 0. If I plug in 1 for x, I get 1 squared. 1 squared is 1. So 1 comma 1 is another point on that graph. And then y equals 2 squared, which is 4. Right, so that's another point on our graph. So we can go ahead and graph those 3 points, 0 comma 0, 1 comma 1, 2 comma 4. And then we're going to, since this opens up, we know that the left side has to look just like this. So we're going to mirror image these guys over to the left-hand side. And I'm going to dot this in. This is not our actual graph. This is the parent function, right? So I'm going to dot it in. I'll actually draw in a solid parabola when we graph the actual function, okay? So that's our parent function. Now what we're going to do is we're going to take all 5 of those points and we're going to move them to create the new graph. How are we going to move them? Well, that's where the vertex comes into play, right? So for the vertex, we've got that little formula, x equals negative b or opposite b. I like to use opposite b. So opposite b over to a. The opposite of b is negative 4. And then 2 times a, which is 2. So we get negative 4 over 2, which is negative 2. So the x-coordinate for our vertex is negative 2. Now remember that the axis of symmetry goes through the vertex, which means that if it goes through the vertex, then the vertex has an x-coordinate of negative 2. It means it's going to hit negative 2 on the x-axis. So our axis of symmetry equation is going to be x equals negative 2. Okay? Now, to find the y-coordinate of the vertex, we can just take negative 2 and plug it into our actual function. So we got to take y equals negative 2 and then square it, plus 4 times negative 2 plus 5. Right? Don't plug it into the parent function, plug it into the actual function, because this is our actual vertex. Negative 2 squared is 4. This is going to be, 4 times negative 2 is negative 8 plus 5. Right? So 4 minus 8 is negative 4. Negative 4 plus 5 is 1. So our vertex is at negative 2 comma 1. Okay? Now, to graph our actual parabola, our vertex is at negative 2 comma 1, which sits right there. Which means that the parent function vertex moved left, so this point right here moved left 2 spots and up 1 spot, right? That means we want every other point to do the same thing. We want every other point to move left 2 spots, up 1 point. So for this point right there, we're going to go left 1, 2, up 1, and that puts us right there. For this point right here, we go left 1, 2, up 1, puts us right there. For this point right here, we go left 1, 2, up 1. And for this point right here, we go left 1, 2, up 1. And so that is our actual graph of our actual function. We're just sliding the parent function over. And then we're done. It's a little bit more work than graphing a line, right? But let's do a few more together and see if we can't make this easy. Okay, next one. All right, first things first. Make sure this guy's in standard form. And he is. Now pick up A, B, and C. A is negative 3, right. B is 0, right? C is, right, 9. Okay? So there we go. All right. We need to know what the parent function looks like. So we're going to create a parent function xy table. The parent function is the adjusted parent function, so it's the parent function with a in it, so negative 3x squared. And I'm still going to use 0, 1, and 2. I'm going to always use 0, 1, and 2, and then mirror image to get the last 2 of the 5 points that I want. Okay, now if I plug in 0 for x, I get 0. This is going to be 0. If I plug in 1 for x, and I'm just plugging it into the parent function because this is a parent function table. 1 squared is 1 times negative 3 is negative 3. And then 2. It's 4 times negative 3 is negative 12. Okay? Now, that's obviously going to take us off the graph. That's okay. So our parent function points are at 0, 0, 1 comma negative 3, and 2 comma negative 12. And if you're paying attention, this is going to be a pretty thin parabola. Remember, a got bigger than 1. The whole number of a, the absolute value of a got bigger than 1. So this is a fairly thin parabola. Now, I made a solid line parabola, and I didn't mean to. So there you go. So that's our parent function. We're going to use those points, to help us create our points for our actual function. But in order to do that, we've got to take a look at this over here. This function is going to open down because a is negative. Where is the vertex? That's where we come down here and we do opposite b over 2a. The opposite of b, the opposite of 0 is just 0, and then 2 times negative 3. So we get 0 over negative 6, which is just 0. So the vertex of our actual function is 0. Now, since the axis of symmetry is a vertical line that goes through that point, that means it's going to hit the x-axis at 0. So the equation for the axis of symmetry is x equals 0. Now, where is the y-coordinate for the vertex? Well, we got to plug that into our function. So negative 3 times 0 squared plus 9. So 0 plus 9, which is 9. So our vertex of our actual function is at 0, 9. So 0, 9 puts us right here, which from the parent function vertex to the actual function vertex, all we had to do is just move up 9. So everybody else is going to move up 9. So this point goes here. This point goes here. This point goes here if you count up 9. And this point goes to here when you count 9. And there's your parabola. Okay? Hopefully that makes a little bit of sense. Okay? All right. Another one for you. And I'll walk through this one with you because there's a fraction for a, which is very scary. So first thing we got to do is make sure that we are in standard form, and we are. Y is by itself. Everybody else is on the other side. Now we need to pick out A, B, and C. So A is negative 3/2. B is 6. C is 2. Okay? Now, let's create our parent function really quick. Parent function is going to look like y equals negative 3/2 x squared, right? It's the adjusted parent function. We're going to use a. Now, normally I would want to use 0, 1, and 2. But here's a trick for you. Since a is a fraction, we want to use 4x multiples of the denominator, multiples of 2. It'll just make our lives a little bit easier. You'll see what I mean in a second. So I'm going to use 2 and 4. Okay? Just a slight adjustment because of what a is. So if I plug in 0 for x, 0 squared is 0. 0 times negative 3 halves is 0. So 0 comma 0 is still going to be one of our points. Then I'm going to plug in 2. Okay? Now watch what happens. 2 squared is 4, right? Oops. If I multiply these two fractions straight across, I make 4 a fraction and make it by making it 4 over 1. I get negative 12 over 2, which turns into negative 6. So by choosing 2, I got rid of the fraction. Okay? And if you do 4 for x, you're going to find the same thing. This turns into negative 3 halves times 16, or 16 over 1 to multiply the fractions together, which is negative 48 divided by 2, which is negative 24. Now obviously negative 24 takes us way off the graph, so it's going to be very difficult to use that. It's all right. 0 comma 0 here, 2 comma negative 6 here, 4 comma negative 24 somewhere down like here somewhere. Okay, we don't have to actually use that. We are going to mirror image the one point on here that we do have, and so our parent function looks like that. Okay, great. That's our parent function. Now let's go take a look at our actual function. Since a is negative, this is going to open down. We saw that from the parent function. And now the vertex. We do x equals opposite b over 2a. Opposite b will give us negative 6 over 2 times negative 3 halves. So we get negative 6 over. Make that a fraction. So negative 6 divided by 2 is negative 3, which gives us 2. Okay, so the x-coordinate for our vertex is 2, comma, now we got to find the y. Axis of symmetry goes through the vertex. It's going to hit 2 on the x-axis, so the equation is x equals 2. So now we want to plug in 2 into the actual function. Oh, I didn't plug it into the second x. Still didn't. Okay, now we get negative 3 halves times 4 plus 12 plus 2. Make that 4 a fraction by putting it over 1. We get negative 12 over 2 plus 12 plus 2, which gives us negative 6 plus 12 plus 2. Negative 6 plus 12 is 6. 6 plus 2 is 8. So the vertex is actually at 2 comma 8. A little bit of work there. Okay, so 2 comma 8 puts us right here. So to go from the vertex of the parent function to the vertex of the actual function, we had to go right 2 up 8. That means every other point has to go right 2 up 8. So land here and here. Now the other point, 4 comma negative 24, is still going to be off the grid, so we can just use these 3 points right here and draw our graph. Okay? All right. Try this one on your own. Stop the video. Start it back up when you get stuck or you feel like you've got it done, and you can check yourself. But we'll walk through this one together as well. All right, so first things first. we are in standard form. A is negative 3, B is 12, C is negative 7. Okay. The parent function, always want to start there. Y equals negative 3x squared. So go 0, 1, and 2. A is not a fraction, so there's no reason why not to go ahead and use 0, 1, and 2. So plug those in for x. We're going to get 0 here. Again, we're using the parent function form to plug in for x because this is the parent function that we're trying to come up with. And then 2. And so we want to go graph those. And then mirror image them. And there's your parent function graph, which is great, but that's not what we want. We want the actual graph. So we come back over here. We see that the A is negative, so this is definitely going to open down, which makes sense because the parent function did. And then to find our vertex, we're going to take x equals opposite b over 2a. Opposite b is negative 12, 2 times negative 3 because a is negative 3. So negative 12 over negative 6 is 2. So the x-coordinate of the vertex is 2. That's also what the axis of symmetry is equal to. So x equals 2. And then to find the y-coordinate, we're going to plug 2 in for x. So negative 3 times 2 squared plus 12 times 2 minus 7. And do the work. So the y-coordinate of the vertex is going to be 5. So just look at the vertex. It's 2, 5. If you haven't picked up the pattern yet, basically the vertex is going to tell you what to do with all of your points from the parent function. 2, 5, they're both positive, so we want to go right 2, up 5 for every point on this graph, including the vertex. So right 2, up 5 puts us at the vertex that we just found. Every other point does the same thing. Right 2, up 5, right 2, up 5. Even down here, right 1, 2, up 1, 2, 3, 4, 5. Right 1, 2, up 1, 2, 3, 4, 5. And boom. There's your graph. Okay? I know it's some work. Okay, try this one. Again, stop the video, start it back up, and look at A. A is a fraction. So when you're choosing your parent function values, make them multiples of the denominator. Make them multiples of 2. Okay. Standard form, yes. A is negative a half. B is 0. It's gone, right? So be aware of that. Okay, parent function, the adjusted parent function, we're going to use A. Again, use multiples of 2. So 0, always use 0. 0 is always going to work. 2 and 4, right? If you plug in 0, you're just going to get a 0. If you plug in 2, 2 squared is going to be 4. And then a negative half of 4 is negative 2. And then plug in 4. Half of 16 is 8. Make it negative, so this is going to be negative 8. Okay? And we want to graph that. Mirror image. And there's your parent function. Okay? All right. How are we going to move it? Well, it's all about the vertex of the actual functions. Now we go back to the actual function, which we see is going to open down because a is negative. To find the vertex, we need opposite b over 2a. Opposite b is going to be just 0 because b is 0. And then 2 times negative a half, 0 over negative 1. So x is going to be equal to 0. So our x coordinate for our vertex is 0. The axis of symmetry is x equals 0. To find the y coordinate for our actual function, just plug in 0. For the vertex of our actual function, just plug in 0 for x. 0 squared is 0. 0 times negative 1/2 is 0. 0 plus 1 is 1. So all we really got to do is shift all of our points up one spot. That's easy enough. This guy goes here. This guy goes here, goes here, goes here, and here. And there's your graph. Okay? I know this has been kind of a long video at this point. If you got it, go ahead and start the homework. But there is one more example that we can get into. So if you want one more shot, stop the video, graph it, and I'll start it back up just to show you, but I won't walk through it. I've walked through a lot with you guys already. If you still have questions after this, come find me and we'll go through it together. There you go. Check all that out. Hopefully it makes a lot of sense. If it doesn't, come find me. Come in during STAR and we'll go through it. Okay, homework sitting out in Canvas. Give it a shot.